Now we'll talk about and revisit the topic of distributed system resonance. We're going to look at a model of an ultrasonic cleaner um, in finite element simulation and describe the different phenomenon and features there. We'll then dig into the design and assembly factors affecting those summary parameters. So this would be helping us to tie those summary parameters back to physical design and what that can tell us about our transducer. Finally, in this section, I'll talk about the equivalent circuit for multiple harmonics. Another feature of a distributed system resonance is not only that the stiffness and the mass is distributed throughout the assembly, and honestly, any device is truly a distributed system resonance, and in certain cases, it can be modeled as 1D, but it really is 2D or even 3D. But how do you take that? So the other aspect of distributed system resonance is that there are multiple harmonics, multiple resonant frequencies of interest. So here I've drawn a two-dimensional axisymmetric model of an ultrasonic cleaner where you have your front mass, you have a back mass, we have what we'll use as a bolt, and some piezo ceramics. If this was revolved around 360 degrees, that would give us our transducer. The reason, and I only revolved it the partial way in order to simplify the simulation. So we'll go ahead into the design, the simulation function, and we're going to first start looking at modal frequencies. But before that, I'll just go into the model real quick. So we'll go into the model and I'll describe what I did here. So I added frictionless supports on these two sides, um, therefore making this apparently, in terms of the results, it will be identical to um, it will be identical to a fully revolved structure. The other thing that I did, there are no other constraints on this. This is sort of simulating the free vibration of this transducer. So we'll go into the results. So modal analysis solves for the natural frequencies of resonance that are permissible in this structure. Now, because of the way I set this up, we won't have any torsional modes, and there will be a limited amount of bending modes. But the longitudinal modes that we're actually interested in for this specific transducer, whereas the ends are extending um, mostly linearly along the axis. Those are the modes of that we'll be most interested in analyzing. For this specific design, and I modeled all the material as steel for this simulation. So the first theoretical resonant frequency was 52 kilohertz, and this is showing here the displacement. So the displacement is maximum, and we can put an animation here too. The displacement is maximum at the top and bottom, and it's minimum near the center of um, our device. Uh, at the place where we do have minimum displacement, we also have maximum stress. That's where you want to locate your piezo ceramics in order to provide the most drive to your transducer for a given voltage. Now, if you put your piezo anywhere along this transducer, you would still be able to provide excitation, but the excitation would be weaker. So you would need to use a larger voltage, which has its own limitations. So you could even invert these colors and say that blue is high stress and red is low stress, because the displacement and stress relationships for longitudinal transducer will in general be opposite. The interesting thing now is looking at a higher mode of resonance, another permissible way that sound waves can bounce off, creating constructive interference or constructive um, amplitude and gain in your transducer. So we'll look at the next mode, and it's very interesting. It's not in this mode specifically. We have significant excitation and movement in the center bolt itself. You will likely not have a strong if you stop that, we won't have a strong excitation from your piezo ceramics because the center bolt here is going to be the most active. This is also a something that when you're designing your transducer, you'll want to exclude or um, design these modes such that they do not operate close to your resonance device. The other aspect about this, and why would we want to be measuring this in general, is because these other resonant modes are sensitive to other interfaces. For example, this is much more sensitive to the center bolt. If you want to investigate properties of the center bolt in our transducer, we can identify a mode of vibration, a mode of resonance, which is more sensitive to that specific component. If you're doing some type of specific analysis, which is very common. Here's another resonant mode at 73 kilohertz, where we have the center bolt apparently pinned at the bottom here. So there's very little displacement here, but it's simulating a free displacement at the top. So there's a pin condition here and a almost a free displacement or maximum displacement at the edge. This is another resonant mode, which also will be found in our impedance analysis. When you do your resonant frequency sweep across these frequencies, you won't have a strong excitation, but because the sensitivity of the piezo, it will excite this mode. Even if it's not the ideal excitation source or placement, the piezo will still excite this mode, and you still will be able to measure its response and the specific frequency. And there are also numerous other modes. Technically, there's an infinite amount of modes which exist. Here's the mode at 84 kilohertz. Here's the mode at 95 kilohertz. As you start increasing in frequency, the wavelength decreases and the complexity of vibration increases. So typically, when you are having a higher frequency, either you are using a higher order mode or you simply just have a small device. So that's which is appropriate then for the wavelength of resonance. The other thing we can look at in simulation is off resonance displacement and actuation. Here I'm using static stress. The specific program doesn't have a frequency response analysis. However, um, driving at low frequency will result in the same displacement levels as driving in static conditions. You can also, depending on your simulation program, you can also use, if you don't have harmonic analysis, you can also use dynamic analysis uh, with reasonable amount of damping and also produce a similar effect to static, assuming you're using low frequency. So here I applied force with zero displacement. I applied forces on top and the bottom of this piezo section. Now the piezo's two crystals, but this effectively you could either provide a positive force or a negative force. Right now, we're just interested in where the stresses and the rest of the device will appear. So I applied forces on top and bottom. There's still the frictionless contacts. So solving this and looking at the other colors in this representation, obviously there's going to be the most stress, or in this case I'm showing strain, so we can also draw stress. There's going to be the most stress inside of the piezo because um, that's the way I'm applying and simulating the forces generated. Not using the piezoelectric effect here, I'm just simulating that using forces, which does add a bias force to your simulation. Um, in order to better understand how the rest of the structure is dealing with this force, we can hide the piezo. And by hiding the piezo, you'll see that the colors have now shifted. So you see where the stress is maximum, where you have large stress. These are areas, and we'll put it also no, we'll deform it. We'll see where we'll have the most influence because this where the stress is and the strain energy is being placed, those are the locations and the places where which will contribute to the capacitance. For example, if you have a very weak joint at your screw, well, that will then allow the piezo to expand further because there's less restraint. So the more ideal your experiment is, the closer it'll be to this design and operation. And the less ideal it is, you'll actually start to deviate, and you may look for problem areas where your capacitance didn't decrease as much as expected, or and you're trying to analyze why that's occurring. You can look into these areas where you have stress concentrations in the static operation, well, which can then give way and a place to start your investigation. So there's a significant amount of stress and deformation right around the piezo, which is obviously expected here. So it's not completely clamping. Um, and additionally, you see we have a static stress being generated inside of the center bolt. So when the piezo expands, it's going to expand the center bolt. When the piezo contracts, the center bolt is going to go under more compression. Due to and in this type of device, it's not held together necessarily like glue, although there is glue or epoxy applied. But due to a DC bias force applied, whatever direction the piezo goes into, whether it's stress or compression or tension, the center bolt will follow along suit. Um, for such a device, if you make center bolt smaller, you'll have less to push against. So you'll have a more free vibration of your piezo. If you did an experiment where you had a very thick center bolt, in that case, the piezo will be more constrained. So your capacitance would decrease further. This is a way of understanding and investigating these results. So here are those results again. Here's the CAD model. Here's the resonance occurring at 50 kilohertz, which is the dominant longitudinal mode. You have stress at the piezo, higher stress at the piezo, so it's going to provide more effective um, oscillation there, more effective driving of your device that will cause your impedance to decrease. Um, because why is the impedance decrease at the resonant frequency here? And why is it the lowest for putting your piezo right at the nodal point? Well, it's because you're driving larger velocity, larger energy in the system, which will in turn provide more internal stress on the piezo, alternating stress, which provides more current. And from providing more current, well, we get a lower impedance. This is also reflective in the electromechanical coupling factor, and we'll talk about that in the next slide. So here's a resonant mode at 60 kilohertz. Again, you can look at the blue, dark blue areas as higher stress regions. Here we have a significant displacement occurring because this is a these are all displacement simulations. In this specific area, you have large displacement occurring in the center bolt. Um, And here you have the center bolt expanding outwards. Each of the resonant modes, in relation to how the piezo here is driving them, will have an appropriate response. The farther away the piezo is from the nodal points, the less coupling and the higher impedance, because the effectiveness of driving will be less. Although you will still see those resonant modes occurring in your impedance analysis. So here's actually the mode of interest where at 50 kilohertz, where we get the most oscillation at the end, specifically this end, where we would then attach it to a different substrate, and well, hence the resonance behavior would change slightly, but it's mainly dominated still by this structure here. Um, but yes, analyzing this model in and of itself, or this transducer, let's talk about a couple of factors. Firstly, this is the dominant longitudinal mode. Usually, the first mode of resonance is the target mode of operation. That's how we traditionally, most often, do design devices. So here in the high stress area, we put our piezo stack. That provides of um, the best level of excitation. So what we're going to find is we have a impedance response at that frequency. It's about 50 kilohertz there, and we'll have an anti-resonant frequency. And for then we can calculate all the summary parameters, including the effective coupling factor, um, including the impedance, or the real admittance. So if we had actually shifted this, and we'll all draw this in red. If we had our stack right here instead of at the original position, and we moved it there, what would happen? Now the piezo is no longer in the highest stress location of that transducer, correct? So the effective driving becomes less. So let's make an assumption that um, the mass and stiffness of the piezo is equal to the mass and stiffness of the rest of the components. um, just so we don't have to worry about resonant frequency. However, because the piezo has mass and stiffness, if you move your piezo away from the nodal location, its mass will be more dominant on the results. So if it's heavier, which usually it is heavier than the rest of the structure, if you move it off that center point, now the mass is going to play a larger role, and it will decrease the resonant frequency. However, if the closer you put a material or a component at near the nodal point, which is a high stress and strain location where you have more strain and stress energy, then the stiffness is going to play a larger role in determining the resonant frequency. Well, let's assume for this argument's sake that we do have similar material properties in terms of mass and stiffness. So what will happen here is that the resonant frequency, if the mass and stiffness is the same, the resonant frequency won't change because the resonant frequency is determined on mass and stiffness, not determined on placement, except in how it affects the effective mass and stiffness. So, so what happens is your piezo becomes less effective at driving. Therefore, your impedance increases because you have less displacement, less energy, and your coupling factor decreases as well. So when we go from A to B, A to B, um, your impedance increases. Your energy in your system will decrease. Depending on your mass and stiffness, your resonant frequency could shift either way, depending on the weight and stiffness of your components. That area that is now you have to fill this part up with steel, let's say now instead of this part. So in the way that affects the natural resonance, that's the direction that the resonant frequency will shift. the next coupling factor will decrease, and the anti-resonant frequency will definitely decrease because it's a signature of the electromechanical coupling. So that's the electromechanical coupling of that specific longitudinal resonant mode. But that being said, the static operation, so if you put your piezo here versus here, the static operation will still be quite similar. You'll still be pulling, you will still be pulling against the center bolt when the piezo expands. It's going to pull the center bolt along with it to expand. It's still going to do very similar uh, um, work against the system at off resonance. So it's a way to perhaps compare those results. When if we understand that if the placement of the piezo doesn't affect the off resonance placement, then you will have similar levels of capacitance between those two variations. However, all these other parameters will change, and this is why I've shown here for off resonance we do have similar levels of capacitance, although they won't be identical. They can be and will be similar and less dramatic than these effects here. We had described an ultrasonic cleaner model to have resonant frequencies at 50, 60, and 70 kilohertz, and then actually beyond that as well. So we'll ask in this slide, how do you model that into one congruent model for the equivalent circuit? So as you can remember, we drew our, if we given a single impedance, resonance and anti-resonance phenomenon, we're able to come up with, using the steps I outlined, an LCR in parallel with a capacitor. But how do we then model other resonant frequencies? The result is actually quite simple. So let's say we have two resonant frequencies. So let's just draw this one axis. We have one here, and then later down the line, we'll draw one there. Notice that they are different in magnitude. Usually, the fundamental has the largest displacement and further harmonics. And these are also very center bolt related. They're not going to be very strongly excited. Therefore, they'll look maybe something like this. Much less coupling, much less drop in impedance from the nominal values. So the way you would represent that is you would do one experiment where you would come up with this for here, and then you do a second analysis where you'd come up with a different model. Right? So you'd come up with what we call L1, C1, R1, and we would come up with L2, C2, and R2. So now you have all this. We have these two resonance circuits. You're not going to simply just connect them because that would strongly change your excitation level, your off resonance characteristics, and your resonance characteristics as well. What you'll actually want to do is figure out how to combine these. So at low frequency, um, you'll understand that you have your intrinsic capacitor. We'll call that C0, or your static capacitance. You'll have C1. You know how we already, this is familiar. You draw the two resonant frequencies, two resonant. No, sorry, the resonant capacitor. Then you'll have your C2 here. So C1 can be determined by, well, your experiment number one. C2 can be experiment by, well, your experiment number two. And you can now use an off resonance value, which is just C, to determine C naught, or the static capacitance. Now you get this value. Then you can directly integrate these two. You can directly integrate those two circuits with your new C node, L1, C1, R1, L2, C2, and R2. And that would give you a final result with two resonant modes at the resonant frequency of him, ultra omega 1, and the resonant frequency of her. So here's omega 1, here's omega 2. As you can imagine from the simulation we did in FEA, you have an infinite amount. But however many you want to consider, you then have to adjust your static or parallel capacitance accordingly in order for all of those to sit well. Because as you pass this frequency, as you pass omega 1, this circuit becomes starts to become high impedance. An LCR circuit has very little current at high frequency. So it practically becomes eliminated once you cross over that frequency range. And in this region here, you'd only have, once you get to this region, you'd only have L2, C2, and R2. So you'd only have these relationships once you have crossed that frequency due to the lower, frequency resonance not responding at high amplitude at a higher frequency. In this session, we covered the method to calculate the equivalent circuit, getting a 1D representation of our piezoelectric response, and beginning to do some analysis and understanding that in one-dimensional terms. Then we looked at summary parameters, which are more useful in general to describe and compare your transducers. And there was significant amount of resonance and anti-resonance discussion, as well as discussion of the coupling factor. And the fact is that you want to you can use some of these as summary parameters actually to calculate the equivalent circuit in different ways. But if you have all these summary parameters, you don't have to kind of debate or decide which method of equivalent circuit to use, or even decide if the equivalent circuit that is valid for your particular transducer, perhaps due to nonlinearity or other effects. You can using your summary parameters is a good way of representing the data, as well as saving the raw data, as well as the plot image trace. I spoke about piezo crystal analysis versus transducer analysis. With piezo crystals, you're looking for material properties. That's why the main difference being the equation for coupling factor is not effective. You don't use the effective coupling factor calculation. You use a more complex number. You use more complex uh, uh, formulas to calculate coupling factor because you're after the d coefficients and you're after you're after the d coefficient in this case, as well as when you're doing the material property, such as just a long bar or a disc. And there are many other piezo resonators there. Um, you'll also calculate. You can also in a closed form solution calculate stiffness parameters or compliance as we typically use in piezo analysis. With transducer analysis, you'll just stick with coupling, with effective coupling factor, and you in almost in all cases don't use them to determine base material properties, except perhaps if you're doing some type of tuning of material properties in FEA. Um, in part two, we took a look at distributed system resonance using finite element analysis and higher order harmonics as well, with the multiple branches of our LCR circuit. We could actually represent multiple resonant modes. In practice, this isn't important to do, but I think it's uh, great for understanding about how these modes play together and into actually contributing toward the static capacitance that if you're analyzing higher modes, you are the parallel capacitance is going to decrease. In the next session, we're going to hammer through several examples and look at different transducers and understand their characteristics and behavior. I will summarize all of the learnings from the last several sessions. We'll make some recommendations for testing commercial devices and give some topics of further study, which may be important to you.